Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a super duper exponential equation with complex numbers. So we have z to the power z equals negative e to the power negative pi over 2, in which case z is a complex number. If you're new to complex numbers, go ahead and check out my lecture videos. I also have another channel that I focuses on real numbers, trigonometry, number theory, and algebra, tiny bit of geometry, and it's called Cyber Math, cyber with an S. Go ahead and check it out and let me know what you think. So to solve this equation, we're going to be using different approaches. My first approach is going to be first writing this as an exponential. Whenever you have something like z to the power w, it can be written as e to the power w multiplied by ln z. In this case, w happens to be z, so z to the z can be written as e to the power z ln z. Or you can just natural log both sides and you're going to get the same result. So left-hand side gives us e to the power z ln z, and the right-hand side gives us e to the power, or it's already e to the power negative pi over 2. Since we have e on both sides, we can basically natural log, and from here we get z ln z is equal to negative pi over 2. This is the critical part because we're going to go ahead and use a special type of function to solve this problem. Okay? So let's go ahead and think about what a could look like, right? On the right-hand side, we have a real number. So how is it possible that you take a complex number and multiply by its natural log, which is another complex number, and at the end, you get a real number? That's interesting, right? So let's go ahead and do some definitions here. For example, if z is equal to a plus bi, how do you define the natural log of z? So in this case, we kind of need to remember how to write a complex number in exponential form, or thanks to Euler, we have a beautiful formula for the polar form of a complex number, which is written as r times e to the I theta. Let me clarify a couple things. R is the absolute value of z, and theta is called the argument of z. In which case, you can go ahead and plot this complex number in the plane. So something like this, like a point, and this is theta. Of course, it's measured in the positive direction. This is the real axis. This is the imaginary axis, so on and so forth. By the way, I go over all of these in lecture videos, so go ahead and check them out if you're new to complex numbers. And in this case, one thing that's super important is that the tangent of theta is given by a over b. So we can basically write tangent theta is b over a. Did I say a over b? It should be b over a. And from here, under certain conditions, we can write theta as arc tangent, which is the inverse tangent. I know that's what they use here in the United States, is given as arc tangent b over a. Okay? But I say under certain conditions because what if this is negative? There are two quadrants in which tangent is negative, so you kind of have to decide depending on the value of a and b. Anyway, so this basically means, like, if you take this complex number and ln it, which is a lot easier to do, obviously, ln z would be ln r plus I theta. Of course, theta, you're allowed to add multiples of 2 pi because it's just the principal argument, and if you make rotations, you'll get multiple values. That's why we call this multi-valued. And there are different branches, so on and so forth. But let's just keep it simple and stick to theta, which seems to be in the first quadrant. Let's just say that for simplicity's sake. And then from here, what is r, right? R is the absolute value, in which case, if z is a plus bi, its absolute value would be the square root of a squared plus b squared. In other words, the distance from 0 is called r, which also looks like radius, right? Because this you can draw a circle by an equation like something like this. Okay? That's the equation of a circle. Whose center is at the origin, by the way? Now, what about theta? Theta is arc tangent b over a. Now, by plugging these in here, where's my equation with the ln and everything? Here you go. We're going to get a nice equation. Not really, but just bear with me on that one. A plus bi. Okay, so how do you find the ln of this number? Ln r, which is the square root of a squared plus b squared, plus I times theta, which is arc tangent b over a. Okay, so this is basically what z times ln z is, and you want it to equal what? Negative pi over 2, which is a real number, by the way. So how do you multiply two complex numbers, or a complex number and its natural logarithm, which is another complex number, and get a real number at the end? That's where the secret is, okay? So let's go ahead and distribute. This gives us a ln square root of a squared plus b squared. And by the way, I forgot to say I squared is -1 because I is the square root of -1, the principal square root. And then we can kind of distribute this, a times arc. By the way, we can do this, kind of factor out an I here, or write the I first, b times arc tangent b over a, and then we can distribute this, plus b times ln square root of a squared plus b squared, but of course there's an I here. And then at the end, we're going to go ahead and factor, and I squared equals -1 gives us a minus sign here, b times arc tangent of b over a. Okay, let's go ahead and put these together, a ln square root of a squared plus b squared minus b times arc tangent of b over a. That would make the real part. And then these two would make the imaginary part. So we're going to factor out an I and then write b arc tangent b over a plus b times ln. We could even factor out an I times b, but I don't think that's a big deal. Ln of square root of this. Okay. And now what are we going to do? We want it to equal a real number, which means its imaginary part will be 0. And factoring out b is a good thing, because if b does not equal 0, then we kind of get something else from there. And of course, this should equal negative pi over 2. So that kind of gives you a system, a ln square root of a squared plus b squared minus b times arc tangent b over a is equal to negative pi over 2. Both sides are real numbers. And this is equal to 0. And if you factor out b and divide by that, you're going to get something simpler. Arc tangent of b over a plus ln square root of a squared plus b squared. And from here, you get 0. Okay? Awesome. This is a system, so we should be able to solve it, right? No, wrong. How do you solve it? It's quite complicated. But if you kind of look at it, this seems to be repeating. So maybe we can call it something like theta, maybe. This can be theta, and this can be theta, and then this can be ln r. But that would be too many variables. Maybe just stick to these for now and see if you can simplify this. So from here, you could probably use elimination, right? Or substitution may work as well. Let's just give it a try. So we could probably, let's see. I could use one of these equations to substitute into the other one. So one thing I can do is I can multiply both sides by b, because in this case, I notice it's going to be helpful because we still have 0. And then we can go ahead and add these equations, and these two will cancel out. And then we're going to have a plus b multiplied by ln square root of a squared plus b squared equals negative pi over 2. Okay, awesome. Now, again, this is something to think about, like how can we solve this equation? There are two variables and only a single equation. Can we make an assumption, say something like b equals 0 or b equals something else? Obviously, it's not going to work. I don't think this is going to get anywhere, but at least we tried. Let's proceed with my more favorite method, which is the second method. Okay, let's just take it from here. We had this, and then after natural logging both sides, remember we got this, right? So I'm going to take it from here. Now, there's a couple of things you can do, one of which is a special type of function, and that's called Lambert's W function. If you don't know what it means, you can look it up, but I'm going to give you the basics. So I'm going to go ahead and switch these around first. So basically what Lambert's W function does is it takes something like t to the t, which is also called the product log, and it just turns it into t. There's no way to explicitly express this. That's why we use w, and we always use this as an input. Like if you ask me, like, what is w of t? We don't know, okay? Unfortunately, there's no way to derive a formula for that, but at least we do know that if we split it up into two pieces, then it's going to be a bijection. Of course, that means we need to talk about two different branches. But let's just keep it simple. But I don't have t e to the t here, do I? Well, I do, but it's kind of hidden. So let's write z as e to the power ln z, and then you'll get the idea. And then the next step is going to be applying w on both sides, obviously. And if you do that, this left-hand side, because this is your t now, is going to give you ln z, and the right-hand side is just going to be w of negative pi over 2. And of course, if you use a calculator like Wolfram Alpha, it's going to give you the solution. I call it a calculator, no more an LLM anymore because it's pretty dumb. But anyways, from here, you should be able to solve for it. And obviously, z would be, because we're looking for z, e to the power w negative pi over 2. But the critical part is, how do you simplify this, right? So let me go ahead and show you how this can actually be simplified. So let's take it from here, ln z times e to the power ln z, we already converted that, right, is equal to negative pi over 2, before we did the w on it, okay? Now, what I'm going to do is basically turn, so left-hand side looks like t to the t, because if you call this t, so I want to turn the right-hand side to something like c e to the c, where c is a constant, because the right-hand side is a constant, isn't it? How do I do that? Well, start by manipulating this a little bit. Don't manipulate people, manipulate expressions, okay? First of all, this is negative 1 times pi over 2. And then remember, I told you I squared is negative 1. So why not replace negative 1 with I squared? I know this is kind of reverse, but you can do that. But what is so special about doing it, right? Well, it's going to help us, because if you split it up, you're going to get something like I times I pi over 2. You may or may not know this, but I pi over 2 is actually the natural log of I. Why? Because I can be written as e to the power I pi over 2. Remember our discussion about the argon plane or the complex plane. If you have a complex or imaginary number like this, you're going to be looking at two things, right? One of them is the argument, the angle. The other one is the modulus, or the absolute value. In this case, it's 1. So we don't have to worry about it. So I can be written like this, which means this can stay, and I can replace this with e to the power something. So let's copy that. ln z times e to the power ln z equals I pi over 2. And I'm going to go ahead and replace I with e to the power I pi over 2. And that's just going to do wonders. You see what I'm talking about? When you do the Lambert's W on both sides, it's basically going to give you what you're looking for. And it's this one. We're going to W here, and I always mess this up, and W here, and it's going to give us the following. ln z is our t here, so it's going to be ln z, and the right-hand side, this is your c. Remember, we said c times e to the c. Do you see what I see? Hopefully you do. And then that's going to give us the following. Okay, what does that mean though, right? I mean, you're solving for z, but remember, z is e to the power ln z, which is e to the power I pi over 2. Uh-oh, that comes up again, and that is exactly I. So z equals I solves this problem, and that seems to be the only solution to this problem as far as I know. But correct me if I'm wrong. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time in another video. Until then, be safe, take care. Don't forget to check out Cyber Math, the Shorts channel, and aplusbi, and bye-bye.